And let's share the screen, and I would go to the first presentation, which is called Lecture 1 Advanced 2021 PPT. So here we are, and I would only briefly recap the basic topics for this course are linear regression analysis, logistic regression analysis, then we will switch into latent class analysis, exploratory and confirmatory factor analysis, and structural equation modeling. So that's only a brief recap, and I would like also to briefly recap that the basic platform we will be using mainly here, and I expect that you will be also using at home for your home assignments, is JMovie. If you decide, you can also select JASP. JASP and JMovie are nearly the same, only I would say the big difference for this course is that in JMovie there is module for latent class analysis. In JASP there is no such module. So for homework assignment related to latent class analysis, JASP is no option for you. And you will also briefly discuss about SPSS capabilities in these procedures. So sometimes I will switch into SPSS and show you how it works in SPSS. And I would say that indirectly, and maybe I will show you also some direct applications, but mostly indirectly, we will be also using R or R project as behind the scene. I mean, behind JMovie and JASP, it means behind graphical interface, there is hidden computation module of R. So we will be using R indirectly mostly, but I can promise that at least for latent class analysis, I will show you also direct computation in our project. So that's basic recap of information. And first of all, I would like briefly, I hope so, recap some your previous knowledge about the concept of statistical testing. Before I start to go into details, I would like only briefly recap that statistical testing is one of possibilities how we can generalize results. And in social sciences, mostly we try to generalize or infer results from the sample, which is only a small piece of bigger population, and we try to infer or generalize from the sample to the population. There is at least some assumption, and classical assumption for possibility to infer or generalize is that my sample is selected randomly. So if I apply random sampling, it is possible somehow to infer results from the sample to the population. And one of classical ways for such statistical inference or generalization is statistical testing. Another approach, I mean classical approach, is to apply so-called confidence intervals. So there are two classical ways for generalization results from the sample to the population if my sample is randomly selected, and once again, statistical testing and confidence intervals. So there are no doubts that these are two options. I guess that from your previous studies, so it means from your previous statistical analytical courses, you know at least a little bit about these possible ways for generalization. I would like also to inform you, and maybe that this information wasn't delivered previously to you, that there is also alternative design for generalization in statistics. Mostly in natural sciences and also in some technical science, they usually do not apply random selection. So it means they do not have big population from which they select unit randomly. But classical design, especially for natural sciences, is based on experimental design. So it means at least that you would divide your units into two groups. One group will be discussed as control group. So it means no treatment at all will be applied to this group. And second group will be discussed as experimental group, and you would apply some special treatment. And if we would like to generalize results from experiment to more units, then there is similar rule to random selection in classical sampling style for social sciences. And this analogy to random sampling in experimental design is called that you make random assignments of units into control group and experimental group. So instead of random sampling of units, you randomly select whether some unit will be control or experimental. And if this condition is satisfied, then you can apply once again such magic such as statistical testing and confidence intervals. So this is how it works. So there are two comparable designs. It means experimental design or classical survey based on sampling. But once again, conditions for generalization is the same: randomization. Randomization for selection into control or experimental group, or randomization of selection from population to the sample. So that's, I would like to say, basic concept of generalization in statistics. And before we start to discuss more, and maybe before we try maybe to avoid some mistakes and misconceptions that you can have about statistical testing, I prepared a small test for you. Don't be afraid of it. So it will not be evaluated. So it means it will not be part of your grade. So it is only for you and also for me, as I will try also to summarize results next time. But before we start, it is maybe good to go through this test, as you will recognize how much do you know about the test. It means statistical test. And I'm not only sure for students who are here in the classroom how I can deliver the link, as for those who are on Zoom, it's quite easy. I can copy it into the chat. So can you also open the Zoom here, or is there alternative? So if you can open the Zoom, it would be nice. So I'll only stop sharing for a second. I will open the chat. Only let me know here in the classroom if I can start with sending of the link. I will add two more colleagues to the lecture. So are you connected or not? Not yet, so I will wait a minute. Let me know. So is it okay? So currently, you should find the link. Maybe I will send it once again for those slightly late. So if you can, please follow the link. And I guess that maximum 10 minutes you need to fulfill the test. Please try to answer by your questions. Please don't try to find some right answers on the internet. And in 10 minutes, I will go back and we will discuss about correct results and also about misconceptions of about statistical testing and p-values. So I will once again recap the link. This once again. So here we are, and before I start, maybe I have a question to all of you. If you previously passed this test, maybe in Czech language, Czech students or not? No students? Yes, I remember that I also use this test for Czech students at bachelor level sometimes. Okay, so you are totally new. Before I start to discuss about results, and then I will try also to download data from your answers and analyze these, and next time we will discuss about results for this study group. I would like only to say that two tests that were included in this combined test were based on two articles. Here is the second one. The article was called "How Confident Are Students in Their Misconceptions About Hypothesis Tests?" Authors were led by Castro Sotos, and it was published in Journal of Statistics Education in 2009. According to my opinion, and I will also try to analyze your answers, this is the best test about statistical testing and p-values, which I know, so that's why I included this test. I must say that more famous is another test, which was invented by German colleagues. Here is original article, Harrer and Kraus, or I must mention that original test was invented by Oakes in 1986, if I remember well, but Harrer Krause applied this test many times, and that's why they are usually related to this test. And the article, as you can see here, is Misinterpretations of Significance and Problems Students Share with Their Teachers with question tag. It was published in Methods of Psychological Research Online 2002. I guess that both these articles can be found online if you like to have this. But before we start to go to tests and correct results, I would maybe like to ask you if somebody could try to define the p-value, as it was the first open-ended question in the test. So can somebody try to define what is magic p-value, which is used for the evaluation of statistical tests? Do you have some hints? As if you would define correctly p-value, it will be quite easy to answer most of the questions in both of these tests, I guess. So some proposals, what could be the p-value definition? What is p-value saying about our results, about our data, about our hypotheses? What is it about? Some proposal, what is p-value? So I will maybe make some bigger letters and try to write down some notes. So what is p-value? Some proposals?
So it's like the probability.
I guess it's probability.
Yeah, of me getting the data that I got if no
Of getting my data, I would say, maybe. Yeah. If
no hypothesis is true.
Yeah, that's perfect definition of p-value. So it is probability of getting my data, and I would add small annex to this. If I get my data or even worse data, it means more contradicting to null hypothesis. As maybe if you remember to some discussion about p-values and statistical testing for previous statistical courses, maybe you applied some normal curve, and p-value was described as the shape below this curve from some point up to the extreme right or up to the extreme left. So this is, if I get my data or even worse data, it means more contradicting null hypothesis. So once again, it is probability of getting my data if null hypothesis is true. That's correct definition of p-value. Thanks for that. And if I try to make some symbols, so usually you can find from statistical point of view, it's not totally correct, but we can take it in social sciences that p-value can be described as probability of getting my data. That's why in brackets I use D as my data, in the condition that null hypothesis is true, and condition is usually after the slash in a probability manner. So this could be technical description of p-value. Before we start to discuss results from previous tests, it is maybe quite good to go into details of this definition. So p-value is not specifically and mainly about hypothesis, but it is mainly about my data. Once again, it's probability of getting of my data or even worse data file. And only null hypothesis is somewhere behind the scene if null hypothesis is true. So it means that p-value is not probability of null hypothesis. It is also, of course, not probability of alternative hypothesis or any other hypothesis I can imagine. It is not probability of any hypothesis. That's necessary to mention at the beginning. So if you say, for example, if your p-value is 0.04, that your hypothesis is valid with 4% probability, that's not correct statement, if you can imagine. So once again, this only probability that I will get data that are not so nice, that would be confirmed with null hypothesis. So that's p-value. So it is mainly about data, and somewhere behind the scene is null hypothesis. Alternative hypothesis is totally out of the scene. There is no discussion about alternative hypothesis in p-value. Let's go back to basic discussion about hypothesis in statistics. What's your conclusion if you perform the test? You can reject null hypothesis and accept alternative one. Alternative hypothesis is not in the definition of p-value, but still you are able to accept alternative hypothesis only if it seems that probability of getting your data, if null hypothesis is true, is very, very low. So then you reject null hypothesis and you say, okay, I will accept alternative one. And just opposite step could be, okay, if my probability of getting my data or even worse data is quite big one, in the shadow of null hypothesis being true, so then I will not accept, but not reject null hypothesis. That's another possible statement based on statistical testing. So if you recap these concepts, and especially the definition of p-value, it would be, I hope so, quite easy to answer the questions from both tests you have just fulfilled. So before we start, I would like to thank you that you participated in the survey. I can promise that also your results will be part of some scientific article based on this testing. So let's go back and I will start with, yeah?
Can I just ask if you can summarize it? If the p-value is 0.04, that means like it is 4% chance of getting my data?
Getting my data or even worse data contradicting null hypothesis. Yeah, that's correct statement. But it's not that it is 4% probability of null hypothesis being true or alternative hypothesis not being true or something like this. Yeah, thanks so. So let's go to this Hiller-Krause test. And I would find the test itself. Here it is. And I will only slightly make it bigger. Once again. So I hope you can read it here in the classroom as well as in Zoom. Is it correct? Okay, so there is only some discussion at the beginning. So it means that there are two groups. Here we have experimental design applied. Once again, we know that if we divide experimental and control group randomly, so that's correct. And here we have some statistical results as if we compare two groups of their means, so we can apply t-test. Here is the value of t criteria. Degrees of freedom is based on number of subjects minus two groups, so it's 18. And for us, the most important result here is p-value is 0.01. Substantively, if we would discuss about these results, this small p-value would mean, okay, it seems there is some difference between control and experimental group in some teaching style, etc. So that's substantive result. But here we have 6 statements that you try to assign whether they are true or not. Let's start with some, I would say, similar patterns in these statements, and let's try to discuss whether they are true or false. So here we have the first one, which is saying you have absolutely disproved the null hypothesis, and here is the description of null hypothesis. And for the third statement, this is nearly the same. You have absolutely proved your experimental or alternative hypothesis. And if we know that p-value is probability of getting my data or inverse data, if null hypothesis is true, we should discuss whether we can absolutely prove or disprove anything. Absolutely. We can prove or disprove something only in the case if we would have all data. In no another case there is such option. So it means that the first statement as the third statement must be false. Yeah? So that's it. Okay. Now I would take the second statement and the fourth statement. Once again, it seems to me that these are like pairs, so it means they are analogy to each other. And the second statement is saying, you have found the probability of null hypothesis being true. So it means you have found PH null. Or for the first statement, you can deduce, it means somehow recompute the probability of experimental hypothesis being true. And if we know that p-value is probability of getting my data or even worse data in the case that null hypothesis is true, so are these statement number 2 and number 4 true or false? So this is also the question for those who are connected via Zoom. So can somebody react?
I think they are true.
True? Once again. It is probability of getting my data if null hypothesis is being true. So it is probability mainly about data. And here both these statements are saying, I found the probability of null hypothesis, or I can somehow recompute probability of experimental hypothesis. So it is saying that this is probability H null or H1. So these two are also false statements. So that's another pair. And now we have 2 more to discuss. It is number 3. No, sorry, 5 and 6, if I remember well. Yeah. Okay. I would say that number 5 is a little bit tricky. You know, if you decide to reject the null hypothesis, the probability that you are making the wrong decision. I wouldn't go into details, but I can inform you that this is also a false statement. And if you would like to find deeper reasoning, please try to find this Haller-Krause article. It is still online, and you can find details in the article. And I would go into the 6th statement, which is also maybe tricky, but it is quite easy to explain. So here it is written that if your p-value, once again, the p-value is 0.01, so if your p-value is 1% or at 1% level, so then you have a reliable experiment finding in the sense that if you would repeatedly take such experiment, you would obtain significant, it means statistically significant with low p-value in 95.9% of cases. These 99 are somehow connected to 0.01, it seems. If you take 1 minus 0.01, it would be 0.99, and in percentage, it is 99. And my question is, whether this statement is true or not. So some proposals, and why is it so? And then I will try to give you simple reasoning for correct answer. You can try, once again. I will not avoid these results. That's also about what you know and what you don't know. So on trial. Maybe you can also try to imagine that if there are 5 statements false, the 6th one would be also false. Okay, so all these 6 statements are false. And the reason for this, I would take reasoning from Gigerenzer article. Gigerenzer also applied this test many times and also make meta-analytic surveys of all results. And the reason from Gigerenzer is following. Let's imagine that you make a toss and you would like to compute the probability that you get 6 points. So if you have classical dice with 6 sides, so probability of getting 6 is 1 divided to 6, I guess, at least if it is 4 dice. Okay, if you take 2 tosses, so what is the probability that you take 6 and 6?
1 to 36.
Sorry?
1
Undivided by 36, yeah? It seems to me. And it is approximately, if you recompute p-value from this, it is 0.03. Okay. And if the statement, such as here, that p-value 0.01 means reliability that in 99% of occasions, you will get the same result, so it means some difference. So if I go back to this tosses of regular dice, so it would mean that if p-value is 0.03 in our case for 2 times 6, so it means that in 97 cases, you would get only 6s if you make a toss with 2 dices. And I expect that that's not correct result. So that's, I would say, very easy reasoning, but also the 6th statement is not correct. So all these statements are correct, and next time I will evaluate the test and we will find how many people were totally correct in the test and how many mistakes you made. But before we go to the second test, I would briefly only recap results from German colleagues that are approximately 20 years old. So here we are, and here you can find results which are percentages of participants in each group who made at least 1 mistake. And here we have original study from Oakes, 1986. It was made on academic psychologists. And you can see that 97% of academic psychologists in British academia made at least 1 mistake in this test. Here you can see that for psychology students who were administered by Haller and Krause, all, it means 44, made at least 1 mistake. But you can go to scientists, so it means to psychologists who are not professional teachers of statistics, and also big majority made at least 1 mistake. And you can go also to those who are teaching methodology in statistics, or who were teaching methodology in statistics in Germany, and you can see that also big majority of these made at least 1 mistake. So it means that also those people who are teaching about p-values, statistical testing, etc., do not understand the concept. The question is whether the concept is so complicated that even teachers are not able to understand, or maybe the reason could be that their teachers were wrong, also their textbooks were wrong, etc. You can find quite nice discussion in this article, which is describing the situation in psychology approximately 20 years ago. And it is also discussed here in this article that even the best books in psychology by which psychologists were prepared to analyze data and statistics were full of mistakes. So that's quite easy to understand that also students and also teachers who are teaching these students are not correct. So that's about this classical, I would say, Oakes test and I would say that very, very good trial to repeat this survey on different groups by Har and Oakes. I can say that similar results were found in approximately 20 studies, so you can find many more articles about this topic. So that's the first test originally invented by Oakes, and now
Did you pass the test? Or
I must admit that the first time I passed the test, I already have the knowledge about the test and the article, so that's not correct evaluation. But I can remember that it was approximately 14 years ago. We also administered this test on the group of professional sociologists, as well as people from Sociological Institute of Czech Academy of Science. And if I remember well, from this group, there were approximately 40 people in the room. It was the seminar about p-value and misconceptions, so none of these people were passing the test correctly. I must say they were totally surprised if I start the seminar about p-value by distributing the test in paper version, and then we were discussing about the results, but still. So I think that this test is not good only for the evaluation, but also for teaching. That's why I'm using it here in this advanced course at the beginning. So we know, I would say, nearly everything about the p-value and related concepts. And now I would switch into the second test, which was invented by Spanish colleagues mainly, in collaboration especially with a colleague from Netherlands. And I would go to the second test. So here it is. And this test is based on 3 questions, and you know that also for 3 questions, so you also added the question whether you are confident or not with your answer. So I wouldn't discuss about this confidence, but here we are. So here is the first one item. Select the definition of hypothesis test contrast that you consider most correct. So it means this is the question. What is statistical test saying about? And here we have 1, 2, 3, 4, 5, 6 possible options. And if I remember well, so comment for all these items is that more than one option can be correct. So here we have that hypothesis test is saying as proof of truth or falseness of null hypothesis, or the same for alternative. So these 2 are paired. Then proof of the probability or improbability of the null hypothesis, once again about alternative. And then it could be assessment of the evidence in the data in favor or against the null hypothesis. And it can be assessment of the evidence once again, analogy based on alternative hypothesis. So proposals, which statements are true and which are not?
Well, I would say all of the statements about the alternative hypothesis are false.
Okay, so that's the first good step. The test is not mainly designed as the test about alternatives, so about alternative are false. So B, D, and F are out of the game, I would say. Okay, so that's the first step. So still we have 3 competitors, and the question is whether all these 3 are right or not.
E is
only
right.
E, as it is saying, it is assessment of the evidence. Once again, if I go back to a definition, it is assessment or probability of my data if null hypothesis is true. Yeah, this is the correct answer here. So only E statement is correct. Okay, so I would go to the second. So here it is. Once again, there is some research design, comparison of 2 groups, and once again, p-value 0.01. P-value 0.01 is not random assigned here, but you can imagine this is the same value as for Oakes test. So this is some similarity between these 2 tests. And now, once again, 6 possible conclusions that could be performed on this p-value 0.01. So it could be the probability of null hypothesis. It could be the probability of null hypothesis being true given the collected data or more extreme is 0.01. It could be the probability of obtaining the same or more extreme data, assuming that null hypothesis is true. It could be the probability of obtaining the data. It could be the probability of committing mistake if we reject null hypothesis. It could be also statement that the difference between two groups is big, and it could be also the difference between two groups is small. So some proposal for correct statements or incorrect statements.
So C would be correct.
This probability of obtaining the same or more extreme data, assuming the null hypothesis being true. So you can, I hope so, see here definition of p-value, as the question is about the meaning of p-value. So this is correct answer.
Yeah.
Okay, so the C is correct answer, and all other are being false. Okay, and the third one, this may be also quite difficult, so I will maybe take it to one page only. So here we are. So here we have the last item, which is not about statistical testing, not about p-value, but about usually predefined level of alpha, or sometimes we call this level as statistical significance. So before we perform the test, we should somehow set up the level for which we could accept mistake. And this is called alpha. So here we have the result of blah, 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 statistical significance for a significance level alpha 0.05. What this alpha 0.05 means. So this predefined level, which is set up before we compute anything and before we perform the test. Once again, this is the first step in statistical testing. We wouldn't discuss why we usually take 0.05. It would be nonsense discussion currently. But once again, here we have 6 statements. So it has been proven that the null hypothesis is improbable. It has been proven that it is false. Or alpha is the probability of rejecting the null hypothesis. The probability of rejecting null hypothesis, assuming the null hypothesis is being true, is 5%. The probability of the null hypothesis is true, assuming it is rejected, is 5%. And the probability that the null hypothesis is true is 5%. So once again, some proposals, which statements could be correct and which statement could be false.
E is correct.
E is correct, and why is it so?
Because significance level tells us how, on which level we can be sure we made the decision. So if we have alpha 0.05, it means the significance level 95%. So if we reject null hypothesis, we can be sure only on 95%. So
okay.
there is 55% chance that we shouldn't have reject null hypothesis.
Okay. Okay. So I would take only for a minute some results for this test. What is it? Yeah. So here we are, I guess. So this is alpha level. So we'll make it bigger slightly. So here you can see that this statement, the probability of rejecting the null hypothesis, assuming the null being true, is correct. For the sample, I guess these are Spanish students, so approximately 42% correctly assigned this. But you can also find that all distractors have quite also big figures, 10, 6, 17, 10, 17, and only 40% selected only this correct answer. So that's about alpha. We can go up. Here it is about p-value. So here, correct definition of p-value selected by approximately 1/2. And if you subtract those who also selected another item, 46 for these Spanish students. And the first question about statistical testing, you can see this was the easiest one, according to test your 62% evaluated correctly this item. And once again, if you subtract those who also selected another item, 56. I must say that according to my own testing, these results are quite nice. Usually I get even worse results. So next time we will discuss about your results as well. So I hope that these two tests and this discussion related to this test could help you to understand for the future that at least p-value is not maybe the best option we can apply in statistics. This is only some, I would say, additional tool to all other results. So at least from this, I would say, short excursus about p-value, you should remember that p-value is not probability of null hypothesis. It's not probability of alternative hypothesis or any hypothesis you can imagine. But once again, it is only probability of getting main data and even worse data if null hypothesis is true. And it is saying nearly anything about these competing hypotheses, I must say. That's why I must add also the information that many statisticians, as well as psychologists, sociologists, and social scientists, and also natural scientists discuss whether we should apply p-value or not. So there is a big discussion whether some official ban should be applied on p-values. So you can find also many articles and also the whole books about possibility to ban to use p-values. So that's maybe, I would say, reverse sides of this coin. If we discuss about p-values and their problems, it is also good to mention that instead of p-values or together with p-values, and I would maybe take this as my favorite, you should also at least compute confidence intervals, as p-value would inform you only reject versus non-reject null hypothesis. That's very easy binary decision, but p-value wouldn't inform you whether your effect is big or small one, whether you should discuss about it or not. If you have big sample, p-value will be also small one and would lead to rejection of null hypothesis. But it doesn't mean that you have found something big. It is only big by sample size. If you take confidence interval, you have also some idea what can be real effect size, and maybe it is more important. So at least if you can compute p-value as well as confidence interval and interpret both of these. So for all our computations here in these lectures, we will be mainly discussing about substantive results and their meaning, about confidence intervals, and we will be also discussing about p-values, but it would be the last important part of results. Maybe that previously you were a big friend of p-values. So currently during this course, I would like to ask you if you can take p-values nearly outside of our analytical discussion. So this is not the most important part of results in statistics, whether we have small or big p-values. So that's I would say nearly the end of this discussion about p-values. So I would go back to the presentation. And here we have only basic recap what I expected to know for this course. So we wouldn't discuss in detail about descriptive statistics. So I expect that you know something about mean, mode, median, frequency table, variance, standard deviation, etc. I hope so, at least by this short excursus today, that you are familiar with statistical testing as well as confidence intervals. And I expect that you know also something about t-test, analysis of variance, about contingency table analysis, and about correlation. We will switch into correlation in the second part today. So we will briefly recap. And I hope that from previous lecture, you know a little bit how to work with Jamovi. And I guess that most of you know quite a lot how to work with SPSS. So we would be able to analyze data. So that's all for this first step. I would make approximately 10 minutes break, and after the break, we would go into the first substantive topic. So it means we will learn how we can perform linear regression analysis, mainly in Jamovi, and maybe that I will briefly also introduce you into computations in SPSS. So some questions so far related to previous discussion, p-values, or maybe some related topics. Okay, so